polynomial degree. Let's say n-dimensional space. So we need n-1 variables to represent it, correct? Or n+1 variable. Yeah. So if I say no, you have to correct it, correct? Okay, that's good. So the thing is, you need at least n values to represent n-dimensional coordinates in this point here. So if you do not have any coordinates at your disposal, what will happen? You lose the values. You lose the values, and in machine learning, we try to lose the values, which is the least significant value in case we go for dimensionality reduction. So do read about it. I'm not going to explain it as of now. If you have doubts, we can discuss that in the upcoming sessions. So that is the point of moving to higher dimensional space and capturing nonlinearity. So what happens when CNN was run on a particular data set, an image data set, you might get some classification accuracy. We discussed MLP, correct? So what is the activation function we use for binary classification? ReLU. Okay. He's saying ReLU. Anything else? Sigmoid. Okay. So is it ReLU or sigmoid? ReLU. Or sigmoid? Think about it. Think about it. What is the range of field? I don't understand. ReLU does not activate all neurons. Neuron activation is a different story. ReLU is what? One neuron at a time. Okay. And sigmoid does the different. Sigmoid activates all neurons. Okay. So what are the equations for ReLU and sigmoid? Can anyone help me with it? Something equations for ReLU, equations for sigmoid. Anyone? 1 by 1 plus e to the power minus 1 plus 1 by 1 plus e to the power minus 1. And ReLU? Okay, the point that I'm trying to convey over here is using, see, if you get confused with what activation function will attend to what, right? So all you have to do is go back to the particular equation and see what are the inputs coming into that particular equation, right? So whatever inputs are contributing to that equation are nothing but the input parameters considered for the activation, right? For any equation, because we'll not always remember like how big the activation function attends to what, right? And there are different tasks for different activation functions. I'm not going to go into much detail because we are running short of time. Right? But then the point was, like yesterday we discussed about sigmoid. Right? We wanted to do a binary, and in class classification we wanted to do a soft max because it gives a some probability range, where the sum of probability is 1. Agree? So far here good. Any doubts so far? Yeah, all here. So let me ask you this question. So if CNN in a single layer is not able to give you a very good feature representation, what should you do to enhance that feature representation? Dimensions or layers? Layers, okay. Okay, he's saying layer. Why should we add layers? So much of complexity cannot be attended in a single layer. Okay. Someone said dimensions. Why dimensions? So dimensions are already dimensions with reference to what? See, when you have dimension, dimension is with reference to your input, and dimension is with reference to your condensed feature that you have. So when do you increase the dimension of input? If the input is not sufficient, you think the input has not captured the data, then you increase the dimension of input. Let's say there is an image, wherein it is like 360 cross 240 image. So the pixels might not be very clear. So you think that image data quality is not good. So what do? You enhance the quality of image. You put HD images on top of it. So better representation can be captured. More pixels are there, correct? But the moment you feel that your feature is not sufficient enough, that your feature vector is not, because let's say yesterday we discussed about that 2 to the power k complexity, right? Sorry, not complexity, 2 to the power k combinations of flip-flop. So each flip-flop, let's say if I have 2 to the power 2, so if I have 2 flip-flops, how many numbers can be contained using that? 4, right? So your feature vector is of size 4. So we get, let's say, of size 2. Then it can only capture 4 combinations. But then say, let's say your data is complex enough that it needs 8 combinations of representation to represent it. So you cannot use your feature representation for doing the task, correct? Right or wrong? Correct? So what do you need to do in this case? Increase your image dimension and increase your feature dimension. Feature dimension, correct. So your feature dimension has to be such that it encompasses, it is able to hold the data, right? But what will happen if your feature dimension is too large? The representation will be fast, correct? Sorry? Drop. No, it won't drop. So we are not getting that. So don't get the thing. Still go one by one. So why will it drop? To say it is dropping, why will it drop if it is fast representation? You meant to say accuracy will drop, correct? Why? No. Time. Okay, time. Forget about time. Let's say we have enough computational resources. Then what do we do? Are we discussing about optimization? Okay. So the point that I'm trying to convey is, let's say we are already on a time crunch. So let's focus on the concept. If you're not able to understand, ask me, I'll explain it yet again. Alright. So my friend here said that we will lose or it will drop. What will drop? Features will drop. How? Dropout layers. Are we talking about architecture now? No, right. We are talking about feature vector representation on it. So dropout is a very different concept. Dropout is used for avoiding overfitting. Correct. So when is your model overfit? When is your model overfit? No. The model overfit when all the examples are so close that the model by hearts the labels. Let's say if there is a skewed data, label 1. 90% of the time it is label 1, 10% of the time it's label 0. So model is clever enough to say that no matter what the input is, I do not need to learn anything, I just write 1. So accuracy by default will be 90%, no matter what, since the data is like that. So that is overfitting. So that is one case of overfitting, correct? So we don't want to discuss about that. We'll go there. We'll go there and we'll talk about vanishing gradient, exploding gradient, all those things. We'll talk about it, but not yet. So far, are we clear about when do we need to increase our image quality? When do we need to increase our feature quality? I mean, when we say feature quality, the dimension of feature vectors, it should be increased. Are we clear about it? Clear? No, not clear. What exactly is our field?
Quality is quality is
The point is, I will rephrase. Just see if you can understand. The point is, if your input data is bad, no matter what training you do, you will not get good accuracy. Agree? When is the input data bad? When the image quality is not good. Agree? There is noise. Resolution is very low. Pixels are not very well defined. Muffled pixel. Right? So to do that, we need to increase our image quality. So that is when we increase our image quality. But then let's say you want to do a 1:2 feature dimension, feature vector, right? Features follow for some seen how a feature looks like, a tensor. Is there anyone who has not used a feature, a tensor, how it looks like? Is there anyone? Show hands. Then I can provide and explain it. Everyone knows how a feature vector looks like, right? Yes or no? No, they don't. Alright. So feature vector is nothing but, see, the moment you load something, right, in a model, it is nothing but you can think it of as an array. Is everyone aware of what an array looks like? Yes? Single dimensional, multi-dimensional array. Everyone is aware? So I just wrote an array over here. Can someone tell me what is the dimension of this? 1 cross 1. 1 cross 4. Okay. 1 cross 4. 1 cross 4 is an array, right? So let's say I just load it to a GPU. We call this array a tensor. That's it. The moment you load it into a GPU, you will call this array a tensor. So far, are we clear? So let's say this array is your tensor, which is going to represent a feature vector. So what is going to be the dimension of your feature vector if you use this array? 1 cross 4. But let's say the image has eight bits that it needs to be attended to. Like so many combinations that the requirement it can only satisfy using 8 bits. So how many bits do we have in our vector now? 4. Correct? So will this vector be sufficient? No, right? So we need to increase the feature vector size. We need to do optimal feature vector. See, yesterday we had a discussion about step size and how that step size might lead to skipping of global minima as well as local minima. So the step size needs to be optimal. Similarly, the input dimension needs to be optimal, and also the feature vector needs to be optimal such that it captures optimally. Right? So now the question is, how do we choose this optimal value? Right? Yes or no? So I mean, in machine learning, there is a term called hyperparameter. How many years of heard that term? Hyperparameter. Okay. So can someone say what hyperparameter really means? Parameter which we need to find. What? Parameter which we need to find for the specific. See, hyperparameter is everyone aware of the term metadata. What is metadata? Data about data. So hyperparameter is the parameter about parameter. Right? You remember like this. So there is a, so you if there is a scaling factor k, right? So you can take any value, but what will be the k value that will be optimal. So that will be experimentally identified for the specific task, right? So that's the hyperparameter. So metadata, just like metadata, hyperparameter is determined with subject to experiments, and then for a certain set of tasks, experimentators found that with these range of values, it works optimally. So we traditionally use that, but there is no hard stop to it. If your task differs, your hyperparameter may change, right? So this is how you find the optimal quality of image and optimal quality of your feature vector, correct? So far, so good. Are we clear with it? Are we clear with the term hyperparameter? Oh, so moving ahead now. Okay, so we have invested enough time. This is thing. So when each layer of CNN was the single layer of CNN was not able to capture the values optimally. Like the clusters were very close. Right? Like me and verifying it. Very close. So it is creating a lot of confusion. So accuracy is low. Is this point clear? Everyone is convinced? So at this moment, let us say we have used the best quality of image available. Right? And we do not have any computation constraints so that our tensors are good enough. So what do we need to do? Add more layers. Each layer will capture what? Each layer will capture what? Features. And along with features, it will capture pixel non-linearity. Pixel values, yes, non-linearity. See, you guys are aware of breaking one function into multiple functions, right? Mathematically. So I'll write it in a very abstract way. Let's say there is mathematical function f1 plus f2 plus f3. There is a mathematical function. Let's say there is a mathematical function f. Can we write it as combination of f1 and f2 and fc? Correct? So this is how you need to think of your model. Your model is nothing but a mathematical function with a hyperparameter. So that hyperparameter needs to be tuned. That tuning is happening during your training. That is why you need to do the training. And when the hyperparameter receives the optimal value, you say the training has completed. So far, so good? Alright. So when the training has completed, what do we do? Testing. So for testing, we'll take some values, we'll do some inputs, and then we'll report some accuracy. That this is the accuracy of our model, correct? And alright. So we'll move ahead with this. So this combination, like mathematical function f can be represented as f1 plus f2 plus f3. Combination done. So far, so good. Alright. And are you guys aware of that sum can be represented as a combination of products? How? let's say you have 2 plus 2 plus 2 plus 2 5 10. Can you say 2 into 5? Can you say 2 into 5? No. 2 into 2 plus 2 plus 2 5 times how much? It's 10, right? 2 into 5 is 10. So you can do it. So let's say there is a mathematical function which is repeating at a certain interval of time. You can represent it using a product. So you can take a common term out. So basically, what I'm trying to explain over here is nothing but the sequence of, if you see the block diagram over there, you will see there is a sequence of convolution operations that are attached in sequence. In sequence meaning, can we break them as product? Yes or no? No. We cannot break them. Because each value has a dependency on the previous one, right? The output of the previous one goes into as an input of the next one. Right? So you cannot do them parallelly. So what I'm trying to introduce concept of is sequential processing and a parallel processing. So if functions do not have dependencies on each other, they can be processed parallelly or sequentially. Parallelly, correct. Let's say basically that is nothing but so what I'm writing over here is the thing makes sense F3 of F2 of F1. Correct? F1's input output is input to F2, F2 input is F2's output is input to F3. Fine. So can you visualize this kind of architecture over there? So this is, let's say there is a CNN block, output of one CNN plus patch normalization plus ReLU is going to be the input for second set of that. We'll do n such combination. So that each CNN captures a feature, but on the condensed feature still, we do the repeat the CNN process. Such that the final feature is way far more condensed and has a denser representation as compared to the original CNN. So the denser the representation will be, we look forward to have a better classification accuracy. So far, so good. Does everyone follow the point? Everyone is clear about what is a dense representation, what is a sparse representation. Clear? Yes or no? I can't hear you. Yes or no? Yes, you guys are aware. Okay. Who is okay with the concept show of hands? Who is not okay with the concept show of hands, please? Because without this, we can't move ahead. You guys are not. You guys are fine. All right. See, the dense representation meaning the vector that is compact enough so that the points when we are you guys aware of a latent representation? Hidden representation, latent representation, latent state. Latent energy. Has anyone heard of the latent energy physics? No. Like the moment you heat your water, it goes to like ice. It goes to a temperature and then at 0 degree. And water at 0 degree, ice and water can be at 0 degree. So there is a delta difference. That is nothing but your latent heat. Correct? So that latent heat cannot, it's not physically visible, but it is there. In a way. So something similar to that, you just look at it as latent representation. Latent representation is nothing but it is the same thing, which is it is just a representation of your image, which is not visible to us. But if you gave the input, machine does not understand your image as the way you perceive it. So it represents the image in terms of some vector. That is nothing but your feature vector. Your feature vector is nothing but a latent representation of your image. Correct? So first of all, so your latent representation is sparse. Sparse meaning what? So let's say this is the latent dimension. Let's say we have a two-dimensional latent space for now. For now, let's say we have a two-dimensional latent space. The points are one. Let's say the points are very close to each other, which are similar. Right? Let's say this is cluster A. This is cluster B. The points are very close to each other, and the points are very far from cluster A and cluster B. Within the cluster, the points are very close to each other, and there is a decent separation between two clusters. So, is this a good representation or a bad representation? Good representation. So, basically, the moment I say dense representation, I'm looking forward for a representation of something like this. The value should be very closer to each other. So, I'm still not going on to the continuity of the latent space. Okay. Okay. This latent space might not be continuous, but then the values having similar labels should be clustered closer to each other. And a sparser representation would be something like this. But within these two values also, there is a significant gap. So that is a sparse representation. Right? So which representation do you think would be good? Dense. Right? So we look forward to obtaining a denser representation. But denser representation can only be captured with the data set fine. Yeah, data is fine. Data is for same data. Let's say keep, now we are all talking about keeping the data is constant. Same data you pass to CNN or you pass to a block combination of CNNs. Which do you think will capture a better feature? Denser ones. Combination of CNN because there is nothing but lot of convolution operations have happened. So after each CNN you got a condensed matrix, correct? So on top of the condensed matrix, again you do a CNN, you get a smaller condensed matrix. Keep on repeating this operation. Keep getting condensed representations. So the final representation that you get, the condensed one. So the images that are similar. So what exactly are you doing? Condensed representation. You're cutting out features, right? So the values, features, the images that are similar to each other, the condensed representation will be very, very close. Is this point clear? Because you're cutting down features, so you are cutting down features. Portion features are similar. Some of the features which are dissimilar, you cut down already. So we went to a compacted representation. Right? So the values will be similar. Is this point clear? Okay. Someone who is not comfortable with this, show hands, please. All right, if you're comfortable, move it. Let's move it. So the point is, we get a compact representation, and that compact representation is nothing but on the screen you can see this is called a resonant architecture. Residual networks. We call it residual networks. So what do we call it residual networks? So with combination, there is one problem that will arise when you go for very long sequence of F1 to F1. If you go for very long sequence, there is one problem that will arise. Can someone identify what the problem would be? So for any length, you have to do what? Backward propagation, forward propagation. More time, okay. Next, anyone else? Complexity, okay. It will be like your loss function will be more complex. Will your loss function be more complex, or the representation that is going as an input to your loss will be more complex? Loss function is constant, right? Loss function is at the end level, it's constant. The representation that is going to your loss will be complex. That is, it will have more number of variables involved, correct? Because we are trying to encompass a higher dimensional space. Is this point fine? Anyone who is not comfortable with this part, especially those who did not attend yesterday, are you guys able to follow? Okay. So let's move ahead. So can you guys think of what would be the problem? This flow. When you do a back propagation, what do you do? You update the weights with what? So there is a loss function. So what do you do to the loss function to get to the back propagation? Pass it? Partial differential with respect to what? Yeah. So the point is rho L by rho Y. But let's say there are three intermediate variables in between. Then could we do a chain rule? Rho L by, let's say rho A, then rho A by rho E, and rho E by rho. Can you represent rho L by rho Y like this? Is everyone aware of the chain rule? Okay. So can we do this? So delta function is nothing but a delta that is coming from each intermediate layer. Correct. And what will the delta value be? What will be the range of the delta value? Rho L by rho something. What could be the range of the delta value? Yeah. What would be the range of the delta value? Differentiation. What could be the range? Any guesses? Any guess? No guess. You don't know. Anyone? You don't want to guess. Let us guess, man. I'm not asking you to right answer. It will either have a value greater than 1 or less than 1. Agree? Do you guys agree? Can it have any other values? Either it will be greater than 1 or less than 1. Can it have any other values? Will the values be negative? Differentiation, will it be negative in this case? Yes or no? No. Someone said no. Okay. Any other answer?
Come on.
Yes. Who is saying yes? Someone is saying yes. So the one who said no, can you please explain why?
Bro, can you remote? Remote.
Why is the provider there?
వెళ్తేనే వెళ్ళప్పుడు ఒకసారి కొట్టు
You don't want to. You don't want. You retain the y, the loss function decreases. So can the loss be negative? So the question is, can the loss be negative? Yes or no? Yes. When the loss will be negative. Does it? What do you mean when the loss is negative? Loss is negative, right? When you train a model, what do you try to achieve? The accuracy of 100%. Accuracy is 100% when y equals y hat. Correct? So what is the loss when y equals y hat? Closer to 0. When the model's accuracy is 100%, what is the loss value? 0. So for loss to be negative, what will be the value for y hat? Greater than 100? Is it possible? So can loss be negative? Agreed. So when the loss cannot be negative, the numerator cannot be negative, can its differentiation be a negative value? What if the denominator has a negative term then? No? Modulus? Okay, so what I'm trying to convey over here is the value is range from 0 to infinity, theoretically. Theoretically, it is range from 0 to infinity. Okay, so I'll just introduce two terms over here. Vanishing gradient and exploding gradient. Anyone who has heard of the term vanishing gradient and exploding gradient? Is everyone aware of the term gradient? What is gradient? See best? Gradient is nothing but slope. Yeah. So slope is tan of theta. What is the theta representing? Angle between what? In gradient descent, what is the tan of theta? Tan of theta is nothing but your slope. The direction that you take the step is in the direction where the path is the steep is. Correct? So that theta will play a role over here. How? Can anyone explain? There is a bit of follow. So far, is there any confusion? No? Comfortable. Then you should answer it if you don't have any confusion. If you have confusion, you answer it. Go back. No? Not following it up. Alright. So the point that I'm trying to convey over here is each of these terms can have a value in the range either 0 to 1 or greater than 1. What do you guys agree? What do you guys agree? Each of the terms can have the values in the range 0 to 1 or greater than 1. I'm saying it can have both, right? Because your loss is always, the value of loss cannot go negative. So the differentiation will give you a term which will be in the range from 0 to infinity technically, depending upon what your function is. Right? For example, if the function is x squared, what is the differentiation of it? 2x, right? Let's say x equals 1. Then 2, correct? X equals 0.5, then 1. If x equals 0.33, then 0.66, correct? So is the point clear that the values can fall in any of those ranges? Correct. So now, can someone tell me what will happen if you multiply a value greater than 1 so many times to it to another value greater than 1? What will happen?
The same value.
No, not the same value. Let's say there is 3 into 6 into some other value 9 into some other value 12. Keep on doing it for let's say 500 times. What will happen? I'm saying do the multiplication 500 times for values which are greater than 1. Let's say 1 into 2 into 3 into 4 into like that till 500 equals 500. What will happen? Any guesses? Are you able to follow? What did you understand? Because I just give you a moment to think about it. That's okay, factorial. Okay, one answer is factorial. What is the other answer? Any other answers? For other values. Blue. That is how you do the computation. What will happen to the final value output? It will be very, very high, correct? So yesterday we talked about flip-flops and bits. Does everyone remember that discussion? Those who did not attend yesterday, question to examine. So are you guys aware of the concepts of flip-flops and bits? No. Okay, think about it as what is the highest number that a computer can store? 2 to the power 16. Why? Because we have 16-bit memory. So if you have 32-bit memory, that is. What will happen if your this multiplication value exceeds that? Sorry? Either out of memory. Anything else? What exceeded? Range is exceeded. So the point that you are trying to convey over here is if any of the terms go higher than the storage capacity, will be able to compute the computation that we want to do. Yes or no? No, we won't be able to do it. So will our model training succeed or fail? Fail. So should this problem be handled? Yes or no? So the question is how do you handle it? Right. So what will you do to reduce the size? Activation. Activation will do what? Then what will normalization do? If that is what activation is doing, then what will normalization do? What will normalization do? The difference between normalization and scaling. Scaling is when you multiply with a factor of a. A can range from minus infinity to plus infinity. There is no cap. When you do a normalization, you multiply with such scale that all the values fall in a particular range. Let us say from minus 5 to 5 is the range. That is the difference between normalization and scaling. Quite clear? Clear? Yes, please hold the time to cover rest, which is a very more complex answer as compared to start. If this is how we go forward, we might not be able to cover it. Please hold it. Till this point, are you guys clear? So what is happening to values are multiplied which are less than 1 consistently. Negative. 0.5 into 0.3 into 0.2 into 0.1 into 0.0 into 0.02. Is it negative infinity? Ever reach negative infinity? I just said you can keep on multiplying the values between 0 to 1 to n range. Like the ones we did for higher value, we exceeded the vectors. Correct. What will happen? Decimal point value. Any other answers? Yes, I would like you to participate in the class. Okay. If you guys don't want to participate, you can go. So those are pretty easy. it becomes close to it. Clear guys? From that section, please. Values less than 1. All the values are less than 1 only. Fine. Somebody from multiply, it will be less than 1. So, what is, let's say the point is the values keep on becoming very, very small, very, very small, very, very small. So, the differentiation will give you a very, very small value, right? And the contribution to the weight will be what? Will be less. How less? Very less. So, will the weights actually update? Let's say if there is a weight of 500, I try to update the value 0.00001. Will it make a difference? Significant difference. Will it make a difference? Will it make a significant difference? Yes or no? Will it make? Yes or no? No, sir. Why? Because the delta is very small. That's it. So it will not make a difference. So will our model be trained? Yes or no? No, model will not be trained. So what will happen if the model is not trained? Our task is the failure rate again. So these are the two cases that we need to handle. So someone said we'll normalize the value in a specific range for the greater than 1 value. What do you do for this case? Same thing. You normalize? Yes or no? You normalize. How many of us do agree that we have to normalize the value in a specific range? Show of hands, please. None of them agree. Then what do you guys agree with? Like, what is your way to handle it? Huh? Adding more bits. Where? Your multiplication is going 0. We are not running out of it. Okay, one solution for higher values, you can add more bits. Go to the 464, 128, 264. Okay. Acceptable. What will you do for the smaller case? The point is, event, you got an event. The feature already has a representation thing that was found on the after this, forget about it. Not from the input vectors. This is the latent representation of input image. The latent representation of your image. Right. For example, let's say you wrote an answer and you gave it to me. Now I'll grade your answer sheet or you, your answer sheet, right? So the answer sheet is the latent representation of your knowledge of the concept. Is this point clear to everyone? Got it, right? Sir. Anyone else? Yes. Section, anyone else? I want to normalize, or when you don't want to normalize. Okay, then what do you want to do? Yes. All right. Okay, so okay, so we already there. All right. So the point is, we have to do something such that that multiplication does not run out of the limit. So basically, what we do with resonate is we skip. If the length is n, what we try to do is we cut short the length. Will that solve the problem? If we cut short the length from n to let's say n by 2 or n by 3, will that solve the problem? Yes or no? How? Length is not, we did not reach that limit. So the values are significantly there. But the question is, will the training be proper if we cut short the length? Finally, we'll answer. Again, it will run out. Yeah. The moment you combine all of them, it runs out of your bit size. Correct? Huh? Divide by? I'm not able to answer. Divide and conquer method will apply for that.
He's telling that if you take the argument that is forward matches.
So it is not addition, it's multiplication. It's 12 by 2 by 2. Okay. And each term, if you look at the thing, it's a dependent term. The moment you cut it, you do not know what is the value to be received. So it's a sequential process, not a parallel process. You cannot do divide and conquer and parallel computation method. Within each block, you can do that, right? Yes. Within each block, whether there are parallel operations required, you can do the divide and conquer. But for this, you cannot do it. So, okay, let me just introduce the terms. Those are problems of vanishing gradient and exploding gradient. Can someone tell which is vanishing gradient, which is exploding gradient? We found two problems, and I am giving you two terms: exploding gradient and the vanishing gradient. So, which is which? Vanishing gradient is the lower value. Exploding is the higher value. Is this one clear? Comfortable? From distance. This is one. So, can you tell me the difference between the exploding and vanishing gradient? And how do we handle them? We just discussed about it 5 minutes ago. Can you tell me? No. And the point is we have escape connections. Okay, I'll just start. I'll just start up the session and explain it. So, escape connection. So, in the right outside that. So, this is called escape connections. So, what we do is, for sometimes we do not backpropagate at all. We cut some layers from between, and that is something what is residual network. That is called resonance. So, that is how the length of n has been cut short. Is that quite clear? That is residual network. Can someone go to the residual network block diagram?
Block diagram?
नीचे वो तो आप कटा हुआ नहीं है
चेक कर रहा हूँ नहीं अच्छा ठीक है ड्रॉप
this is nothing but your residual network block. Residual network is nothing but you skip some layers from between. You just pass this particular way to some additional way. So what will happen is, so what is the point of doing forward pass and a backward pass? Can someone tell me? What is the point of doing forward pass? So the information flows, correct? What is the point of doing the backward pass? So as that the output for the loss is getting minimized, correct? So in the forward pass, what do we do? Skip the connection. So if you skip the connection, you cut short the path is cut short. But still, since the length is so high that even if one block is cut in between, it does not make much of an impact to the information flow. Do you agree? So this way we handle both problems. We reduce the length as well as we handle the information flow. So far are we good? This is resonant. Hence, resonant features. This is resonant 50. This is resonant 50. There are multiple variants to it, and then there is a dense net. Dense net, what they do is they connect first layer to second layer and first layer to third layer. So first layer to all the layers, then second layer to all the forwarding layers, third layer to all the forwarding layers. That is nothing but a dense net representation. So that is the major difference. There are a lot of representations that come into picture. Each of those representations will give you nothing but a feature vector. What do we do with this feature vector? That is the question. So once the feature vector is there, we have a compacted representation of your image, which is fed at the CNN. Correct? Please. Yeah. Still a part of discussion? Okay, then explain to me what is the difference between density and resonance. Which are features? So who should he ask? How many times have we asked that? Is everyone clear enough answer? How many times have we asked? Okay, what is the problem? Go ahead. You follow? Variance? Gradient? Vanishing gradient and exploding gradient. Okay, guys. Is everyone clear with the concept of exploding and vanishing gradient? So who can explain to him? Like he is not able to understand vanishing exploding gradient. Can someone explain? Who's it? Can you please explain? Who is it? Please explain. Dilip will explain it. So Dilip will not write your exam, right? So the point is, will the value increase? Even it's nice. W1 is later. But the vector is very, very low. It kept on multiplying that. It was which stored or vanishing? Vanishing. Vanishing. Any keyboard giving 1 kg, there is a limit. After that, next one. Certain exploding rate. If you keep on starving it, and die at some point. So that is vanishing rate. Understood? Alright. So far, okay. So this is nothing but a shift connection block. This is clear? Alright. So this is where we close for the day. And when you have the features, we discussed MLP yesterday. Right? MLP, we discussed yesterday. Who can explain MLP to me now? You guys, you guys are aware of MLP? You were different yesterday. You guys are aware of MLP? Yes or no? Yes or no? Is everyone aware of MLP as a concept? Multi-layer password transfer, what it does? It is nothing but a dense-layer compact representation for your input feature vector, which will be passed on to your classifier. Correct? Yes or no? Same thing you will do with your result feature as well, and then you will do classification. But this is your object classification task. Did you guys get the list of projects by any chance? So, what are projects do you have? Object detection, face recognition, image recognition, and pre-rate. One is object detection, other is face recognition. What is that? Image recognition. Face recognition. Image classification. So, for those of you guys who want to do a classification project, are you aware of how do you need to do now? Is the point clear? What will you guys do? Steps, can someone tell me? First is raw image. Raw image, what will you do? Feature extraction. Using what? Using? Okay, CNN. Okay, CNN or husband. Whatever. Then next one. Next is what? Next is classifier. Classifier will be built using. We discuss one classifier so far, MLP based classifier. We'll discuss other classifiers as well. So for now, we can use an MLP based classifier with any of the activations that you want to use. Is it clear? Can you close that? Any doubts? Any doubts so far? Because you see, the concepts are keep on getting complicated as and when we move forward. So if you do not go up, you will not understand the following section. I'm not going to mathematical details for the same reason that I want you guys to understand the concept. Is the point clear? Are you guys comfortable with resonant architecture? And why is it better than CNN? Yes, you can take a form. You can take a form. No. Am I clear? All right, then. Thank you for bearing with me for today. And next day, we'll discuss how exactly is this entire matrix going to be used for object classification. So today, what are the points we discussed to summarize? Can someone tell me? Vanishing gradient, exploding gradient, resonant nonlinearity. Why does model versus algorithm? Why does resonant capture better features as compared to CNN? Feature dimensions, limitation capacity, all this. Okay, all right. Thank you, and maybe you can pass it.